Hi everyone. Lesson 2.6 is going to be a short lecture. The reason for that is we're going to look at integration by use of tables. And when I say tables, I mean they show you integrals of a function, and they have kind of a predetermined integral that's been calculated, and it could be any number of ways that they've calculated it. So in terms of material, there isn't a lot to show in this lesson. It's more about examples and having you become familiar with it. So I've included the integration tables within your formula sheet, okay, and I've posted your formula sheet on LMS. So what we've done so far is we developed integrals for key terms. We talked about sine and cosine. The natural logarithm function was a big one, especially when we talked about partial fractions. As well as obviously higher order, binomials, trinomials, especially when we got into partial fractions. But sometimes they don't fit within those nice kind of neat packages or those key terms. And that's where these tables come in. And what these tables show is, like I've said, they show integrals of a specific function that follows a certain format. So it's not going to be, the table isn't going to show you x squared over 2x plus 1. Okay? What it does is it lists it in a general form. Okay? And it uses up to 3 variables. 2 values that are a constant value, a and b are what they're labeled as. Not all of them have b within them. Okay, some of them do, some of them do not, but they're both constants, a and b. And then the function, okay, whether the function is, x squared or 2x plus 1, blah, 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 that is listed as u. Okay, so I've given you an example here. This is actually, if you go to the tables that are listed in your formula sheet, they're also in Appendix B of your textbook. So that's where I'm taking the clippings from that you'll see in the formula sheet. So the integral as shown, let's say the first example is the integral of u divided by a plus bu. Okay, so I've color coded them to match the colors I have here, so you can kind of see the difference. And what they do is, in this case, you have a certain function u twice, and you have 2 constants a and b. And what it does is it gives you a predefined integral that you then plug those values in to find the answer. So the key aspect of this question, there's 2 parts to it. The first part is looking at it and identifying which integral it falls under from the tables. The second part is identifying each part, identifying the a, the function u, and the second constant b if it's applicable here. So our first example is, I'm just going to show you how it fits in. X cubed over 4 plus 3x cubed. So this falls within the format that I've shown here, where you have the function u in both spots, x cubed and x cubed. So your function u is x cubed. Your constant a, in this case, is 4, and b is 3. So using the table, you know that this is the integral. It provides you that. So you can simply substitute the values in. So it becomes 1 over b squared, which is 1 over 3 squared, multiplied by the first brackets is a plus bu, which becomes 4 plus 3x cubed, minus a, which is 4, times the ln of 4 plus 3x cubed, the same term. Okay, so all of your kind of legwork to solve this comes back to figuring out which integral it is in the table and then substituting the values in appropriately. Okay, so I have 4 examples that go through different spots in these tables, and you can see that they're numbered. So when they're numbered in the table, I'm going to write which number this one corresponds to. Okay, so after these 4 examples, what I'm going to recommend is that you do a lot of practice to get used to these, okay? Don't expect that you're going to have a lot of these questions on your test, okay? There might just be one of them that shows up, all right? But it is important for you to be able to find them quickly. Okay, so let's look at our first example. Evaluate the integral of x squared times the square root of 2 plus 3x squared dx. So what I'd like to do in these is try and pick out, first of all, what I think the constants are and the function, and then I want to try and match it to a function that's in these tables. So for each of these questions, I recommend you have the formula sheet available to you, and you're kind of looking, because I'm going to pick out the function that I believe is appropriate using the same number that you'll see in the table. So what jumps out at me, first of all, is I see 2x squared terms, one of them having a constant behind it, 1 naught. And then I see a second value that's just a number here. So my first suspicion that I see is that I have two constants, a and b. And a is usually the standalone constant. B is normally the constant that's behind a function. Okay, so that's an important distinction to know. And then lastly, I have a function u. So starting with u, I see that x squared is in here twice. So I'm suspecting that the function u is x squared. Because there's a constant behind one of the x squared terms, I have a funny feeling that the function, or the constant b, must then be 3. And our last constant, which is a, would be 2. The reason I say it's not always the case is there are functions that have something like u squared plus a squared, or a squared minus u squared, something like that. So sometimes the value for a could actually be the square root of what's listed here. Again, that comes down to just looking at these tables and looking at the different functions. So the other item I can see here is a lot of the functions in the tables are fractions. So it's one function divided by another. So in this case here, it is not set up like that. So that means a lot of these functions can actually be disregarded. Okay. So what that leaves us with is, for the first grouping of 8 functions, there's only one left. It's function number 5. Okay. For the second grouping, you can see that most of them don't fall within it, except for functions 14 and 15. So the 3 forms that I can kind of see are 5, 14, and 15 to what it could possibly be. As I go down further, you can see that on our next page of formulas, none of those, with the exception of 19 and 20, fall within that regard. But 19 and 20 both have a function to the exponent 3 over 2. So that doesn't work here because we have a square root. So a square root is actually to the exponent 1/2. Okay? The last sets of groupings for formulas 29 to 43 and 44 to 52 focus on trigonometric and exponential functions. They don't fall within this realm here because we don't have either of those there. So in a relatively short period of time looking at those tables, I've put it down to 3 functions. So starting with the first function, function number 5, okay, we see that in function number 5, we have the integral of u times the square root of a plus bu. And then that's equal to an integral, okay, which is negative 2 times 2a minus 3bu times a plus bu to the 3 over 2 divided by 15b squared. Okay, that is the integral. Okay, so I'm writing that exactly as it shows in the table. And when I look at it here, well, I've got, if I were to substitute in what I suspect to be my values, I get the integral of u times the square root of, I've set 2 to a, and the second function, I've set b to 3, and x squared to u. Okay, So you can see that it follows the same pattern as this when I substitute it in. So without having to look at 14 and 15, I know that this integral fits the formula. Okay, so once you do this legwork, I've written out this integral, you simply substitute your values in for a, b, and u into this equation. Okay, so that means the integral becomes negative 2 times, this is 2 times a, which is 2, minus 3 times 2 times u, which is x squared, times 2 plus b, which is 3 times u, x squared, to the exponent 3 over 2, divided by 15 times b, which is 3 squared. So now it just comes down to simplifying. Okay, so that's the same as negative 2 times 2 is 4. Okay, and in this case, minus 3 times, this what I wrote 2. This was actually b here, so this should have actually been 3. So 3 times 3 is 9, x squared, multiplied by, this one is the same, 2 plus 3x squared to the 3 over 2. And this is divided by 15 times 3 squared. Well, 3 squared is 9. So we have 15 times 9, which gives us 135. Now, what the tables don't show is plus a constant, but I mean, they've omitted it on purpose if you actually look at what was shown in the textbook. So we can simply add a constant. When it comes to doing integration by use of tables, because the tables omitted the constant, if you don't show it for this question, it wouldn't be something I would take marks off for. Okay? Okay, so let's look at our second example. Evaluate the integral of 1 divided by y times the square root of 9 minus y squared dy. Okay? So a couple things jump out at me here. Okay, I always start by writing a, b, and u. In this case, remember I said b is normally the constant that sits behind the function u. So I see two items here, a y and a y squared. But in both cases, I don't see a constant sitting behind it. So I'm suspecting here that b is 0. In other words, it's not existent. The other thing I notice here is we have a function y and a function y squared. Okay, so what that normally means is in your formula, okay, you might see a function u. In this case, we can call it y. And you sometimes will see a u squared. In this case, we would have y squared. So you can see when you have one of them to the exponent 1 and one of them to the exponent 2, that's often the case. The second item to pay attention to is when you have something, okay, like 9 minus y squared, okay, whether it's in the square root sign or it's not. When you have one of them as squared, it's usually what it means is if we suspect that it's u squared there, which we do, it's normally written as something like a squared minus u squared, or u squared plus a squared, or some combination of those. It's not usually written as u squared plus a, or in this case, a minus u squared. So what that means is these are not normally how it's written in any of these integral tables, that the number 9 is probably a squared. Okay? So what that means is a would be the square root of 9, or 3. Okay? So something to keep in mind there. Knowing all these variables, we can substitute them in and we can see what we come up with here. Okay? If we do that, all right, if we substitute in for y's, we get the integral of 1 divided by, we know that y is u, times the square root of a, in other words, a squared minus u squared. Okay? If we do that, what we end up with is, looking at these tables, do we have any of them that are 1 over the square root of a squared minus u squared? times u? We do. Okay, looking at it, formula number 13. Okay, so 13 is listed as the integral of du divided by u times the square root of u squared plus a squared. And if we do that, that's equal to negative 1 over a times the ln of a plus the square root of a squared minus u squared divided by u. So you can see in both these examples how complicated these integrals are. That's why they're given in table form. This seems complicated, but I'm simply copying it directly from the tables. Okay, so I'm not expecting you to know how to integrate that. I'm just expecting you to be able to recognize which variable is which and substituting it in accordingly. Okay. If I do this, then what I end up with is negative 1 divided by a, which is 3, times the ln of a, which is 3, plus the square root of a squared minus u squared, which is 9 minus y squared, divided by u, which in this case is y. Okay. Again, the one item that your table doesn't show is it omits the plus a constant. Okay. So remember, that's just simply substituting our values in. I didn't do any other, I'm going to call trickery in this question or anything different. Okay. Okay, so let's look at our third example. Our first two focused on more binomials and functions with fractions and exponents. This third example focuses on trigonometric functions. So let's evaluate the integral of sine of 3x sine of 2x dx. So the big thing you notice here compared to what we've seen in our integrals so far is these are when the sine functions are actually different. Okay, one has 3x and one is 2x. So when you're looking at the integration tables, the third section, which is identities 29 to 43, focus on trigonometric functions. Okay, as you do more examples, you'll see how each of these fits within the list of tables. So in this case, again, we're looking for a, b, and our function u. Well, the only function in here other than the sine function is x. So I think it's safe to say our u function is simply x. Now, looking at a and b, we have two sine functions and two different constants behind the function x. So in this case, being the only two functions, I'm going to set a to 3 and b to 2. Okay? And automatically in this case, du becomes dx. Okay? Because all we're doing, we're not actually removing anything within this integral. Remember when we did substitution rule, there was often a piece that we were removing. In this case, we're simply substituting in purely to be able to look at the tables. If we substitute these values in, we get the integral of sine of, instead of 3, we write a, and instead of x, we write u. And we get the sine of, instead of 2, we write b, and instead of x, we write u and du. Okay, so now we have a form of this function. And if we look, there's a couple options here that involve two trigonometric functions. The ones that stand out start at function 39 and go to 43. So functions 42 and 43 are similar to the next lesson you're going to see, where they have exponents. So sine of some exponent of x, cosine of some exponent x. Okay, we're not going to use those. But in 39 to 41, if you look specifically at 39, 39 shows the integral of sine of au sine of bu, okay, which is exactly the same. Okay, so we must know that this must be the integral. And again, the advantage to this is now it just becomes a simple plug and play exercise. So the integral of this, according to our table, is the sine of a minus b times u. divided by 2 times a minus b minus the sine of a plus b times u divided by 2 times a plus b. So the key difference between these two is one is adding the two a and b terms together, one is subtracting them. So now knowing what a, b, and u are, we can simply substitute them in. And if we do that, we get the sine of 3 minus 2 times, instead of u, x, divided by 2 times 3 minus 2, minus the sine of 3 plus 2 times x, divided by 2 times 3 plus 2. And that is obviously plus a constant, which is not included in these tables. So if we simplify these, 2 times 3 minus 2 is simply 2. So this becomes 1/2 times the sine of x, because 3 minus 2 is 1. Minus, in this case, we have 2 times 3 plus 2, which is 10. So that's minus 1 over 10. Times the sine of 3 plus 2 is 5, which gives us 5x plus a constant. Okay? So this is integrals for sine functions, again, from 29 to 43 on the integral table list. Okay? Our last example, evaluate the integral of x cubed ln x dx. So we see a ln function, or a logarithm or exponential function. And those appear in the tables starting at 44 to 52. Okay? So I'm giving you kind of where to focus on depending on the type of integral. In this case here, all right, we have an x cubed function and we have a ln of x. Well, luckily in our tables for number 46, it's the only one with a ln function. And what that says, okay, I'm going to do this the opposite way only because we actually only have one function here with a ln. So I want to see whether or not we think it's going to fit. And what it says, it's integral number 46. And it says the integral of u to the exponent n ln u du. And it's equal to u to the exponent n plus 1 times the ln of the function u divided by n plus 1 minus 1 divided by n plus 1 squared. Okay? So what this is saying is we have u to the exponent n. We don't have constants here, a or b. So a and b are both non-existent. But in this case, we have a function u raised to an exponent and ln of that function. So if it's going to fit within this, the function u must be whatever is sitting in the ln function. So u must be x. And to look at whether or not that works, the function before it, okay, it has to be the same function x raised to an exponent. In this case, it is, right? It's x raised to the exponent 3. So our value for the exponent n is 3, okay? I know we talked about a and b in the function u, okay? But when you'll see exponents, you might see a term like an n, but it'll only show in the tables as something like this raised to an exponent, okay? So if it's never there, you never have to consider it. And it's really only in the case where you're raising something to an exponent. So knowing this, knowing that it fits into here, we can now substitute in our values just to double check, okay? So we have that 3 is n and x is u. So if we take our example here, we get the integral of, instead of x, we write u, and instead of 3, we write n. And we have the ln of x, which is the function u, and du. Remember, we're doing purely substitution one for one, so du is dx here. So these two match, meaning that we can now plug and play these values into our solution here, which is provided from the table. And if we do that, we get u, which is x, to the exponent n plus 1, which is 3 plus 1, times the ln of u, which is x, divided by 3 plus 1, okay, which is the exponent plus 1, minus 1 divided by, in this case, 3 plus 1 squared. And that again is plus a constant, which is not in the tables. If we simplify this, we get x to the exponent 4 times 1 over 4 ln x minus 1 over 16 plus a constant. Okay? So again, once you solve for which one it is in the table, the integral grows very fast. So that was all I had for this lesson. Again, I said it was a shorter lesson. I highly recommend that you look at these practice problems and try them. The more of them you do, the faster you're going to get at running through these tables. Okay? If you have any questions, please ask in the tutorial or just send me an email. Thanks, everybody.